Welcome to Dr. Jett's continuing series on calculus. Today's lesson is section 4.3 from Rogowski. Rogowski combines two concepts which I don't think are exactly the same into one section, but we'll do them both because they're both relatively short. The mean value theorem and the first derivative test. First we'll talk about the mean value theorem. It's related to how functions change and how the derivatives change, so that segs very nicely into whether a function's increasing and decreasing and how the derivative's related to that. Then we'll talk about the more probably practical part, the first derivative test, which is used to find local maxes and local mins. And then, of course, some examples. So first, the mean value theorem. The mean value theorem says, well, suppose f is a function that has a derivative. In this case, it's similar to the previous section. It's on a closed bounded interval ab, but we're going to use this interval more explicitly. So the function has a derivative on this interval, which is to say, it's continuous on the interval, and its derivative exists not necessarily at the endpoints, but everywhere else. Well, if that's true, there must be a place in between a and b where the derivative at that spot is equal to the slope of the line between a and b. So here's a graph. Here's a, and that's f of a. Here's b and f of b. If you take those 2 points and you found a slope like that, that's what they're talking about in the mean value theorem. That's the slope we're interested in. And this theorem says there must be some place on the graph with that slope. There are 2 such spots here, as you can see, approximately. Somewhere in there there's one, somewhere in there there's one. This function doesn't say how many spots are like that. It says there has to be some spot like that. Why? Well, think about it. In order to go from here to here, you gotta go up. If you gotta go up, you gotta flatten out at some point. Or maybe you just go straight across. However you do it, you're gonna have to have a spot where you flatten out, or start to flatten out, at the same rate as between A and B. Now, if you look at that, there is a corollary to this. This corollary is kind of subtle, but it's actually pretty powerful. What it says is, let's look the other way around. Suppose this is always 0. Suppose the derivative is always 0 between A and B. If it's always 0, well, there's always a c that has this true. That means this has to be 0, which means this has to equal this. What does the corollary say? It says, suppose a function's derivative is always 0 on an interval. Well, that means the endpoints and everything in between has to be the same. If the derivative is always 0, the function is constant. Maybe that doesn't seem like a big deal, but it's actually quite powerful, and we'll use it a lot later. But for now, I want to talk about what derivatives talk about in terms of increasing and decreasing. If a function's increasing on an interval, what does that mean? Well, it means it's going up. If you think about it, going up means this. It doesn't mean the derivative is increasing. It means the derivative is positive. I say greater than or equal to 0 because there could be some spot where instantaneously it's 0, but it continues on. So these are essentially interchangeable. If f is decreasing, what does that mean? It means the derivative is negative, although there could be instant points where it's equal to 0. It can't be 0 for a whole point, for a whole interval, because that would mean, of course, the function's constant. Barring that, though, there can be little spots where it stops for a second and then continues on. Now, how can we use this concept to talk about where there are local maxes and mins? Well, look at this. Where are the local maxes and mins? We defined that in the last section. What is a local max? Right here. Right there. What about local mins? Right there. Right there. Well, those, of course, are critical points too. And we learned last section, in 4.2, that every local max, every local min is at a critical point. But we don't know which ones are which and whether there could be extra critical points too. So how can we tell if it's a max? Think about this one. It is a max. Why? Because it's the biggest. But also, because it got bigger over here, and then it got smaller over here. So let's take a look at that. What's going on here? The derivative is positive. What about here? The derivative is negative. If you look over for this max, the same idea. Right beforehand, the derivative is positive, and right afterwards, the derivative is negative. And in fact, let's take a look at this whole thing. This whole thing is negative. This whole thing has positive derivatives. Right? Because we find all the places where the derivative is 0 or doesn't exist, the only other choices are positive and negative. So we can use these pluses and minuses to determine whether or not we have a max or a min. That's the first derivative test. What is the first derivative test? We first find all the critical points. Formally, what we're going to do then is put them on a number line. This will split the number line into regions. Each region will have a derivative that's plus or a derivative that's minus. And using those pluses and minuses, we can figure out which ones are maxes and which are mins, and if there are some others. So let's do an example. Talking about it's not the way you do it. Doing it's the way you do it. We need to find the critical points. We want to find the maxes and mins on here, the local maxes and local mins. How do you do it? You take the derivative. Hopefully that derivative is not too challenging. Sorry, that's a minus there. Minus 12x squared and the 1 goes to 0. We need to know where this is 0 or doesn't exist. And similar to an example from last time, there are no does not exists. They're actually fairly rare. They don't happen that often. So we need this is 0. I can factor a 4 out of that. I can factor an x squared out of that, in fact. So that makes that x. And that makes that 3. So we get 4x squared is 0, or x minus 3 is 0. So that means x could be equal 0, or x could equal positive 3. We're not done. Those are critical points. That's not mins and maxes. And maybe they are, but we don't know yet. They might be. They might not be. We're not sure. So we make a number line with those two values. And we're going to use them and check the derivative elsewhere. How many regions do we have? There are 3 regions. These numbers separate your points very nicely. Make sure you put them in the right order. You can get really screwed up if you, say, put the 3 over here by mistake. How do you check these? Critical points are where it's 0 or where it doesn't exist. So every single other spot has to be a positive or a negative. So let's try one out. Something in between here, 1's a good choice. Something over here, -1. And something over here, I don't know, 1,000. It doesn't have to be any particular value. It can be any value you want. Some are easier to calculate. And remember, all we care about is whether it's plus or minus. So we put this into the derivative. -1, now here's the derivative right here. Or we could put it in right here if we want. Either works. I like the second one better, because look at this. 4 times x squared. Well, if we start with any x except 0, that's positive, right? So positive times whatever, we don't care. X minus 3, put a -1 in there. I don't know what value necessarily it is, but that's negative. Why? Positive, positive, negative, multiplied together, you get negative. Put a 1 in. Positive, positive, negative. Put 1,000 in. Positive, positive, positive. Now, remember what we talked about. When the derivative is negative, the function's decreasing. So I'm going to draw a line like that. When the derivative is negative, the function's decreasing. And when the derivative is positive, the function's increasing. Visually, what happens? The function's going down, it kind of stops for a second, then keeps going down, then it goes up. It's decreasing on this whole region. It just stopped for a second there, but it keeps going down. There is no max or min here, but there is a min here. There's a local min at x equals 3. Later, when we graph it, when we put the function on the graph, we'll actually want to know what the value of the function is. So we put 3 back in here and go, I don't know, 3 times 3 times 81, whatever it is. But right now, we just need to know where it is. This is how you do it. Let's try again. A slightly harder function. And you might be looking at that thinking, ugh, I can't do that derivative. But you can. We've done this derivative. Well, not this one. We've done ones like this. Something times something. This is a product rule. 1 times ex squared plus x times, what's the derivative of e to the stuff? It's e to the stuff times the derivative of that stuff, which is 2x plus 1. Now that may look ugly, but actually, It's relatively easy because there's an e to the x squared everywhere. I'll factor that out. And what do I get? 1 plus 2x squared plus x. If I want that to be 0 or not exist, then I can find the critical points. And again, this one has no does not exist. If you want a does not exist graph, you sometimes have to work harder. They're not as interesting for derivatives. They're harder to find, and mostly we do this part. That part is important, but mostly we do this one. Now, there's two things multiplied together. So that means the first one could be 0, or the second one. I'm going to rewrite this in the standard quadratic order. Now this, e to the stuff is never 0. So I use that symbol to represent there are no solutions to this. There are all sorts of ways you can write that. You could write dne, there are none. This one, I don't know if that factors. I don't think it does. So, what do you do when you have a quadratic that doesn't factor? You use the quadratic formula. X is minus b plus or minus square root of b squared minus 4 times a times c, all over 2a's. Now, before I go on, I'm checking it. Yeah, that's right. Look inside here. This is all negative. Square root of negative doesn't work. There are no solutions here either. So, there are no solutions to this function. There are no places that are critical points. No critical points at all. Still a number line, just nothing on it. I want to check the derivative. Well, how many regions do I have? With no critical points, I have one region. I need one value. Plug 0 in. Plug 0 into here. I see it's positive. This is a function that always goes up. And that means there are no local min or maxes. We're running out of time, so let's do one more quickly about a quotient. Here's a function. I've already taken the liberty of taking the derivative and looking for all the critical points. You can do that in your own time if you want. I want to plug into the derivative. I need some spots to plug in. And where do I plug them in? I plug them into the derivative. Why? Because I want to know if the derivative is positive or negative. Look at this derivative before we go on. The bottom is squared. It's not going to be negative ever. So in terms of whether this derivative is positive or negative, all I care about is the top. Put a 0 in there. I see that is positive. Put a 2 in there. That's negative. Likewise, this is negative. And what does that mean? When the derivative is negative, the function's decreasing. When the derivative is positive, the function's increasing. And one more. When the derivative is negative, what happens? The function is decreasing. Actually, this should probably technically go to there. How high does it get? I don't know. I'm just drawing arrows to get a visual representation. The graph doesn't actually go boink, 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 but it has that sort of curvature in it. Can you tell now where the maximums and minimums are? I hope you can. There's a local min. Local min at x equals minus what? Oh, minus 1. Local max at x equals positive 1. Again, we would ultimately want, where are the graphs? But you know what? Where on the graph are those functions? We plug it in there. But right now, all I want are these. If you can do that, you're doing good. This is Dr. J.